Chapter 5, Section 3, Part 1, Inverse Functions. Some of today will be a review, since you've worked with inverse functions in Algebra 2 for sure, and probably in Pre-Calc also. So let's review. If we have a function, f of x equals x plus 4, then here are some of the points, ordered pairs in the function, 1, 5, 2, 6, 3, 7, 4, 8, etc. The inverse of f of x, which is denoted f to the power of, looks like a power of -1, but what that means is just the inverse function of f equals x minus 4. So the ordered pairs that would be in the inverse function would be 8, 4. See how that corresponds to 4, 8. 7, 3 corresponds to 3, 7. 6, 2 is from 2, 6, and 5, 1, and 1, 5. So notice that the range, the y values of the original function, are the x values in the inverse. That's the domain of the inverse. And the domain of the original function is the range of the inverse. So the reflexive property of inverse function says that the graph of a function contains the point AB if and only if the graph of the inverse function contains the point BA. And if you remember from geometry, if and only if means you can read this sentence forwards and backwards. It could say that the graph, if the graph of f inverse contains the point BA, then the graph of f contains the point AB. And it also is true the forward way. If the graph of f contains the point AB, then the graph of the inverse of f contains the point BA. So the definition is a function, this is the definition of the inverse. A function g is the inverse of the function f if you put the function g inside of f, like a composite function, and you simplify it and you get x. And if you do it the other way, where you put the function f inside of g and simplify that, you also get x. That's the definition of what an inverse is. So you would use that to verify if two things are an inverse. So let's do that. Show that f of x equals 3 minus 4x and g of x equals the quantity 3 minus x all divided by 4 are inverses, and we're going to show it analytically. So that means we're going to do f of g of x, and what should we get? We hope we get x. And then we're going to do g of f of x, and we hope we get x. That's how we show or verify that they are inverses of each other. So f of g of x means we're going to put the function g of x in place of x in the f function. So 3 minus x over 4 is going to be inside of this spot right here. So we're going to have 3 minus 4 times, I squeezed those in too much. Let me rewrite that. 3 minus 4 times the function g of x. 3 minus x all over 4. So let's simplify that. These can cancel. And then we'll have 3 minus the quantity 3 minus x. And remember to distribute the negative. So it's 3 minus 3 plus x. That will simplify to x. Okay? Let's do the same thing with g of f of x. We're going to put the function f of x in place of the letter x in the g function. So it's 3 minus x, use parentheses whenever you're doing a composite function, all over 4. So it went in place of this x right here. F went in place of x. So if we simplify in the numerator, we're going to have a 3 minus 3 plus 4x, because we're distributing the negative. Continuing to simplify the numerator, we get 4x over 4. And then canceling those 4's, we get x. So we've verified analytically that these two functions are inverses. Let's talk about what the graphs look like. Oh, first let's talk about the domain and range of f and f inverse. The domain of f, since this function has no issues with plugging any x value in, it doesn't have a square root, it doesn't have a denominator that can't equal 0, the domain of f would be all reals. And what about the domain of f inverse, which is g in this case, we're calling it? Also, no issues. So the domain of f and g, or the inverse, are all real numbers. Issues are, what I'm talking about for issues are if there's a denominator that can't equal 0. This denominator of 4 is never going to equal 0. If you have a square root, or if it's a trig function where you're going to have a denominator where that cannot equal 0. Things like that. Look for things like that. All right, let's talk about the graphs. Being slow today. So the red graph is the line 3 minus x over 4. And the black line is the line 3 minus 4x. The dotted line is the line y equals x. Notice how these two graphs, the red and the black, are symmetric with respect to the line y equals x. So if I fold this graph on this line, this would match up with that, and this would match up with that. So they're reflections over the line y equals x. So that's how the ordered pairs flip. The domain becomes the range of the inverse, and the range becomes the domain of the inverse, because they're reflected over the line y equals x. So all of the y's flip to be x's, and all the x's flip to be y's, and anything that's on the line y equals x remains the same. So that's how you can show graphically that two lines or two functions are inverses of each other, if they are reflections or symmetric over the line y equals x. Does every function have an inverse? No, it does not. Theorem 5.7 says that number one, first of all, in order for a function to have an inverse, it has to be 1 to 1. That means, okay, a function, first of all, has to pass the vertical line test, where you drop a vertical line through and it only crosses the graph once. But for the function to have an inverse, you have to be able to pass the horizontal line test. Number two, the function is strictly monotonic. So a function only has an inverse if it's strictly monotonic, which means it's always increasing or always decreasing. If this vocabulary is new to you, make sure you write it down, because it will be coming up a lot in calculus. Strictly monotonic means that a function is always increasing or always decreasing on the entire domain. Then we call it 1 to 1, and therefore it has an inverse. So does this function have an inverse? We know it's a function, passes the vertical line test, and if we throw some horizontal lines on here, they all cross only once. So yes, this function would have an inverse. However, this function would not, because there's a place where it crosses more than once. A horizontal line crosses it more than once. So this fails the horizontal line test, so no. And you notice it's not strictly monotonic. It increases here, but decreases here, and then increases here. So it's not strictly monotonic. This one is, because it's always increasing. The rates that it increases are a little bit different sometimes, but it's always increasing. So does this function have an inverse? I don't have a graph. How can I tell? That's where calculus comes in. If we want to know if a graph is always increasing or always decreasing, we can take its derivative. So the derivative of x minus 7 to the third power is the derivative of the outside. Oh, sorry, working too fast here. Times the derivative of the inside, which would just be times 1. Sorry, let's complete the whole chain rule. And then the derivative of 6 is 0. So the derivative is 3 times the quantity x minus 7 squared. How is the derivative going to help us tell if a function is strictly monotonic? Well, remember the derivative, whenever it equals 0, is where the graph could possibly change from increasing to decreasing, or vice versa. So if we set this equal to 0, divide by 3, take the square root, we get x equals 7. 7 is our critical number. It's the place where the graph could possibly change from increasing to decreasing. So let's analyze it. Let's choose a number here like 0. If I put 0 into the derivative, because I want to know if the derivative is positive or negative, I want to know the slope of the graph. If I put 0 into the derivative, 0 minus 7 is negative, but you square it and you get a positive, and then times a positive 3. So the function is increasing here because its slope is positive. Pick a number like 8. If I put 8 into the derivative, 8 minus 7 is positive 1. Square it, you get a positive, and again, times a 3 is positive. So if my slope is positive, that means the function is increasing. So did the function change from increasing to decreasing or vice versa at 7? No, it did not. We know that the graph must be increasing on its entire domain. Because the derivative is always positive. So does this function have an inverse? Yes, it does. On page 346, there are some guidelines for finding the inverse of a function. Again, this should be review for you. Determine if the function has an inverse. That's the new thing. Solve for x. Switch x and y. Define the domain of the inverse to be the range of f. And then verify. So this is the step where you come up with the new function. And you can actually do, instead of solving for x, you can interchange x and y first and then solve for y. So these two are kind of like interchangeable. I don't care which way you do it. So let's do this example here. Find the inverse of f of x equals x cubed plus 1. So if you want to rewrite this as y equals x cubed plus 1, and then solve for x, so we subtract 1, and take the cubed root of both sides. X equals the cubed root of y minus 1. Then switch your variables. And then just rewrite this as the inverse notation. So the inverse would be the cubed root of x minus 1. Okay? And then we would graph it. Ta-da, here's my graphing calculator. So go to y equals and type in x cubed plus 1. And then in y2, we're going to do the cubed root. Oops, I just need math. Number 4 is my cubed root of the quantity x minus 1. If you don't have the update, you've got to use parentheses around that whole thing. And let's do a zoom 6, because I don't remember what my window was. Okay, now imagine that line. Oh. Sorry. Imagine that line, y equals x here. If we had a line y equals x, imagine how that would look there, y equals x. Is the inverse the reflection of the original function? And it is. Your homework is page 349, 1 through 39 odd. We'll be having a memorization quiz tomorrow on the 6 trig integrals on page 339. So make sure that you review those, memorize them. I will give you the integral, like integral of tangent x dx, and you have to write down what the answer is. And that's all from memory, no notes, no calculator. If you don't like your grade, then you can retake it as many times as you want on your own time.